Good morning, students. Welcome to today's lecture on Chem 101. Our topic today is electronic configuration of elements. When we are in secondary school, most of us we are taught this topic, although some of us have forgotten, maybe as out of one thing or the other. Like I told you that at this level, what we'll do is try to bring you back to the things you've done. Probably you didn't do them in details, but then we'll refresh your mind and your memory. Let's do a little introduction on the topic. In chemistry as a science, when electron configuration of elements are mentioned anywhere, what comes to our mind is the description of how the electrons of those elements are distributed in their atomic orbitals. In other words, simply showing how the arrangement of these electrons are done in orbitals, how they are arranged. That is what comes to our mind. I know when we were in secondary school, we were taught what a periodic table is all about. So it's not strange when we use those terms. But remember that periodic table is just the arrangement of elements in an order of their increasing atomic number. When Mendeleev constructed the first periodic table, he said it is the arrangement based on its relative atomic number. But as time goes on, we now realize that it's increasingly a sort of increasing atomic number. So you have to have that in your mind. Now there's a picture there. If you look at it right there's a picture there, electronic configuration formula and energy level. So now you have the energy level. This energy level is trying to pay more emphasis on the shell. We have the subshell. We have the shell, which is the KLOMNO shells, which can be represented by 1, 2, 3, 4. You know. Then we have the subshell, which is the 1x, 2x, 3p, 2p, 3s, 3p, and etc. If you can see, it's on the board there. So whether you call it the KLOMNO, you can also represent it with the energy level 1, 2, 3, 4, and etc. Now, let's look at the next slide there. The processes applied in distributing these electrons in orbitals. When we want to distribute electrons in orbitals, whether you are talking about the KL, whether you're talking about the LO, MO, NO shell, or we are talking about the subshell, there are procedures or processes which will help us to do it with ease. Look up there. You can the first one, you can start with the shell number. That shell number, you find out the shell number you want to distribute the electron. Which number is that? Remember that the shells, each shell has different radius from the other one. The distance from K shell and LO shell and MO shell differs. So if you are to measure, if you get an atom, get the radius from the nucleus, get the radius, you can see that what it will take you to cover distance from the nucleus to K shell differ from what it will take you to cover distance from the nucleus to L shell, it also differs from what you take you to cover distance from the nucleus to M shell. So that is why we put that one, then number of shell. And the simple formula which you're going to use to do that is you can use the formula 2n square. Use the formula 2n square. So that n there only stands for the number of shell. So if you're talking about K shell, you know that the number is 1. So what you do is you replace the n with 1. If you're talking about the L shell, you know you're talking about 2. What you do is to replace the n with 2. In other words, if you want to get that, you have to get 2n squared. That is, you replace the 2n with 2 and get the answer. So that will give you the maximum number of electrons, the possible maximum number of electrons that are expected to occupy that shell. So you don't just have to put any kind of number you want to. You check this shell you want to put these electrons. How many number of electrons are expected to be there? So if you are confused, as in, if you can't remember, just use that formula to calculate it. If you compute it, it will give you the number, which will now help you to do what? Know what you're going to put in a particular shell. Then the next thing you can follow with the type of shell. First, what type of orbital do you want to put this thing? Is it the first one, K? Is it L? Is it M? And etc. You know the type of orbital you want to put the electron. Because that should come to your mind. That should be in your mind. Where do I want to put this electron? Which orbital do I want to put this electron? Where is it supposed to be? Then the next one there, the next step there is that you now use a superscript to indicate how many electrons are in that orbital. Like you now said 1x2 or 1x1, 2x2, 2p, 2, 3, 4, etc. So you use that superscript to indicate that, to show it. If you're talking about the shell, not the subshell, you can use this formula I've given you. It will simply tell you how many number of electrons that you're supposed to put in a particular orbital or in a particular shell. So the process continues. Now, there is another thing that I want you to have in mind. One of the major processes you can use is to get the different period or blocks in the periodic table. If you check a periodic table, check the period or check the block. If you have a periodic table with you, you can see there are some blocks and there are some periods. Now, if you go to the block, for example, if you go to period 1, group 1, you can now realize that in group 1, you find out the total number of what? The number of atomic numbers in the element in group 1. Whether it will show you whether what will be there is only x orbital or it's going to get up to p orbital. So if you just study the periodic table very well, you can see where they write blocks. So you now realize that group 1, probably what you're going to get is the block, S block. Group 2, you might get up to only S block 2. Group 3, you can also get up to P block, XP block. So these things are explained in the periodic table. So it will help you to know the number of electrons you are supposed to put in the particular block or a particular shell you want. Then you have I give you an example there, like you have the 1x, 2x, 2p, 3s, 3p, among others. These are electronic orbital energy level. An atom, listen, I want you to understand that an atom has as many electronic orbitals due to which energy level or can be categorized according to their specific quantum number. Now, some of you might be asking, what is even the meaning of this SPDF? I just put the meaning there so that you have in mind. That is where it was derived when scientists are getting these quantum numbers. The SPDF is an abbreviation. S is for sharp, P is for primary, D is for diffuse, and F is fundamental. Remember that at this level, we may not teach you some of the elements that you can get in F block because those ones have higher atomic numbers. And at this level, we don't want to bother you with those ones that belongs to the F block. But you can pay attention the ones that have, especially the ones that belong to X and P block. Is very important. Now, I want us to bear in mind that an element location on the periodic table can be used to determine its electronic configuration. What do I mean by that? If you go and check a particular element in the periodic table where it is located, it is easy for you to say this is its electronic configuration or to help you to draw its electronic configuration. It's simply by following the order of the period, the rows and the block, just as I've mentioned. You have 1x, you have 2s, 2p, 3s, 3p, 4s, 3d, respective, etc., etc. Now, some of the examples of elements, because when we're talking about elements, I believe we'll still remember what, as a scientist, you should know what elements are all about. I just decided to put some of the examples on the screen so that you don't look as if, especially some of you that don't have a strong knowledge on chemistry in your O level. We have elements, examples like the hydrogen. We know the hydrogen, it has atomic number 1. We have the helium, which is 2. We have the lithium that has atomic number 3. We have the beryllium. We have the boron. We have the carbon, which we are familiar with, especially when we want to talk about organic chemistry. We have the nitrogen. We have the oxygen that we make use of every day in our life, that we breathe in and out. We have the fluorine. We have the neon. We have the sodium, magnesium, aluminum, silicon, phosphorus, sulfur, fluorine, argon, potassium, and calcium. So I decided to just pick this small number so that I will not bore you, I will not input so much stress in your brain. But if you can be able to know how to get the electronic configuration of these few elements I've mentioned, I think it will go a long way to help you, because it is still the same process or the same procedure. So that is just the whole thing. Now, sorry, what is there is the first 30 elements. You can correct there, the first 30 elements and their atomic numbers. So I want us to look at the first 30 elements, then look at the atomic numbers, look at their shells, and look at their subshells. This is number 1. You have the atomic number. The number 1 element you have there is hydrogen. You can see, remember that every element we are mentioning or you come across, try as much as you can to note down its symbol, because sometimes in exam or even some books you read, they may not write the name of that element in full, they can use the symbol to write, they can write the symbol. So it's for you to know that this H, anywhere you see it in chemistry, we're talking about elements, stand for hydrogen. We don't have two elements that share the same symbol. Then hydrogen has atomic number 1, and if you go to electronic configuration, is under the subshell, you now realize that that 1 belongs to 1x1. That's where you cannot get it. That's where it belongs. Then you have the valency 1 because the electron outside at the atmosphere is only 1. Then electronic configuration for the shell is also 1. That's what you have there because you cannot get anything more than 1 electron in hydrogen. So if you take a look at the second one there, the atomic number is 2, and the name of the element is helium. The symbol is He. So I wouldn't want you to confuse the symbol with hydrogen. Remember, this one is He. The first one is H. So sometimes when you ask students to write the symbol of helium, they'll write it H. Maybe because it started with H. But when you write it H, just know that automatically you failed it. Because what you have there is He. Then, if you go to its electron configuration under subshell, what you're going to get here is 1s2. That 2 atomic number, that's what you have there. It belongs to the 1s, the X block 2. Now, then we go to the, if you go to the electronic configuration of the shell, what you're going to have there is 2. That's what you're going to get. Then, number 3, we have the element with atomic number 3. That's lithium. Lithium has atomic number 3. Now, if you go to 1s, what is the electronic configuration subshell? What you're going to get there is 1s2 and 2x1. Now, look at it that lithium has entered the 2x, but with 1 valency electron as 2. So if you go to its electron configuration in the shell, that is the K, you're going to get 2, L is going to be 1. Now, we go to the fourth one, the element that has atomic number 4. That is the beryllium. Now, just look closely. This beryllium symbol is Be. It is not B. I want you to know that because number 5, you have the boron. It is B. The four is Be. So note that it's not when you're asked to write the symbol of beryllium, you now write it B, or already know that you failed that. So if you look at the electron configuration in the subshell of beryllium, you're going to get 1h2 and the 2h2, giving you that 4 atomic number. That is what you're going to get there. Then the valency electron for beryllium should be 2, because that 2 is the one, the electron that is at atmosphere shell. Now, if you are to arrange it in the shell, what you're going to get is KL. That is 1, 2. All you're going to get is 2 and 2 in the main shell. Then if you go to number 5, you have the boron. The symbol there is B. I don't know if you understand what I'm saying. The symbol there is B. Then take a look at its electronic configuration under the subshell. You're going to get 1s2, 2s2, and 2p1, giving you the atomic number 5. That is the 2 plus 1 is 5. That is atomic number of boron. So if you are asked to arrange boron as an element in its electron configuration in subshell, that is what you are expected to do. That's what you're expected to do. Then, if you go to the valence for the electronic configurations for shell, what you're going to get there is 2, 2, 3. That 3 there is a valency because that is the last electron you can get at the outermost shell. That is 3. That is the valence. That's all you see that valence there. Then, number 6 in the screen, on the screen there is carbon. We are very much familiar with carbon. We are very familiar with carbon. Then if you were to look at the electron configuration of a subshell of carbon, what you're going to see is 1s2, 2s2, and 2p2. If you add 2 plus 2 plus 2, it gives you 6 atomic number. That is the number of electrons you can get in that carbon. And if you are to go to the electronic configuration in the shell itself for carbon, what you're going to get is 2 at the K shell, then 4 at the allo shell, giving you the valency of 4, because 4 is is what the electron you can see at the outermost shell. That's why you get the valency at 4. Then, if you were to go to 7, the element that has atomic number 7, what you're going to get there is nitrogen. Remember vividly that nitrogen has its symbol as N. It has its symbol as N. Then let's look at the electronic configuration of this nitrogen. You're going to get 1s2, 2s2, and 2p3. That if you are to add it up or you sum it up, we're going to get 2 plus 2 plus 3. That is 7, giving you the atomic number of nitrogen. Then, if you are to go to the shell itself, what you're going to get there is 2 and 5, giving you 7. There's a mistake there. The valence should be 5. Then, if you go to oxygen has atomic number 8, and the symbol is 0. It has atomic number 8, and the symbol is 0. You can see the symbol there. Then, if you were to take a look at the electronic configuration of this oxygen under subshell, you're going to have 1s2, 2s2, and 2p4. If you are to sum them up, that is 2 plus 2 plus 4, that is 8. That gives you the atomic number of oxygen. And if you are to go to its electronic configuration on that subshell, the valency, a lot of them should be 6, because that's the one that is at the atmosphere. There's a mistake there. Then you have what you're going to feel is 2, 6. 2, 6. The K shell is 2, the L shell is 6. Now, let's look at the fluorine. Let's look at the fluorine. The fluorine as an element has a symbol F. It has a symbol F. Now, if you were to arrange it using electronic configuration subshell, what you are going to have there is 1s2, 2s2, 2p5. That is to say 4 plus 5, giving you 9. Then if you go to the electron configuration, you're going to get 2 on the K shell, and 7 at the L shell. I want you to ignore some of the things. I'm going to explain to you what happened to those valencies, but pay attention in the electronic configuration which you are treating. You have the 2 and 7. The 2 will come into K shell, and the 7 will come into the L shell. Then, if you are to go to, if you go to, if you go to the neon, if you are to go to neon, which is the 10, the one that has 10 atomic number. Neon has a symbol of Ne. Neon has a symbol of Ne. Remember that neon is quite different from nitrogen. It has a symbol of Ne. So if you are to arrange it in sub-shell, its electronic configuration, you're going to get 1s2, 2s2, and 2p6, giving us 10. That is 2 plus 2 plus 6. That is 10. Then, if you are to put that neon in the shell, in the K element shell, what you're going to get there is 2 and 8. So if they write the 8 there, it simply means that nothing is remaining there. It doesn't give out any electron. It does not give out any electron. That's why it's 8 there. That is why it's 0. It is a noble gas. It is inner gas that is relaxed. Then if you go to atomic number 11, atomic number 11, what we'll have there is the sodium. Sodium. Remember that the neon has a symbol as Ne. Some of you confuse neon and the sodium, the symbol. The symbol for sodium is Ne and not Na. I want you to note that one down. It's Na and not Na. If you were to look at the electronic configuration of that sodium there, you're going to see 1s2, 2s2, 2p6, and 3x1, giving us 11. That is, if you add the 1s plus 2s, that is 4, plus 2p6, that is 10, plus 31s, that is 11. It gives us atomic number of sodium. Then, if you go to its shell, you want to arrange it according to the KL shell. What you're going to see there is 2 will be in the KL shell, L shell will be 8, and you will now have 1 at the MO shell. That's the valency electron there will now become 1. Then let's look at number 12. Atomic number, element that has atomic number 12 is called magnesium. We are very familiar with magnesium. So it has its own symbol. This symbol, why I put the symbol there, or why I'm emphasizing on the symbol, remember I said that even when you're trying to balance an equation, you may not get the full name of the element that is involved. You get them in symbol. So the symbol of magnesium is Mg. That is the symbol. So anywhere you see an element will write Mg, know that we are talking about magnesium. So if you are to look at its subshell in electronic configuration, you're going to have 1s2, 2s2, 2p6, and 3s2. If you add them all up, you're going to have 2 plus 2 is 4. 4 plus 6 is 10, and plus 2, giving us 12, giving us the atomic number of magnesium. Now you go to the shell itself. If you go to the shell itself, want to arrange according to K element shell, what you're going to get there the K shell will have 2 electrons, the Lo shell will have 8, and the MO shell will have 2. The valence, the last, the element, sorry, the electron at the atom shell is 2. That's why the valency is 2. Then the next one you can see, according to on the screen there, is 13, the element that has atomic number 13. That is what we call aluminium. We are all familiar with aluminium. Every day, most of the things, materials we see around us, the ones we use in doing vehicles, the ones they use in building houses, there are some, so that particular element, we are very familiar. Even if you not come across, but at least you heard some people talking about aluminium. Now, the symbol there is Al. Al, that is the symbol. So anywhere you see the symbol Al, they are talking about aluminium. Now, if you are to look at the electronic configuration under the subshell, you're going to have 1s2, 2s2, 2p6, 3s2, and 3p1. Let's add it up. If you were to add them up now, what you're going to get, 2 plus 2, that is 4. 4 plus 6, that is 8. Sorry, that is 10. Then plus 2, that is, sorry, plus 3, plus 2, that is 12, and plus 1, that is 13. Giving us the atomic number of aluminium, 13. Then if you were to take this aluminium to arrange them in KLS MOL shell, what is going to take there is 3 shells: K shell, Lo shell, and MO shell. So if you are to put it in this shell, what you're going to get is 2 electrons will be found at the K shell, 8 electrons will be found at the Lo shell, and the 3 will be found at the MO shell, which now becomes the valence electron, the one at the atom shell. Don't worry, we're going to talk about more, pay more attention on this valency, maybe, so that some of you will not be confused. But pay attention on the electronic configuration, which is what I want you to pay attention. I'm going to treat valency and explain more about valency as a topic, so that if you hear about the valence, let it not be, it sounds so strange to you. Now, the next one in the line there is the element that has atomic number 14. The element there is silicon. Silicon is a very important element. We use it every day. They use so many things. So it has a symbol Xi. So when you hear or Xi in elements in chemistry, symbol of a particular element called a silicon. Now, if you are to look at the electronic configuration of this silicon, you're going to get what you have on the screen there is 1s2, 2s2, 2p6, 3s2, 3p2. If you add them up, you're going to have 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, and plus 2 again, that is 14. That is the atomic number of silicon. Have you seen how it is arranged? So it's very easy. Then, if you go to take them, you want to arrange them in shell, KLOML shell. If you take it, you want to arrange them in KLOML shell, you're going to know that in each KLOML shell, you will see that it is the KL shell for silicon. You have 284. 284 will be found in the K shell for silicon. That's what you're going to get in the silicon. Let's look at it now. That is 2 at the K shell, 8 at the LO shell and 4 at the NA shell, at the MO shell. Now go to atomic number 15. Element that has atomic number 15 is phosphorus. I know some of us are familiar with this element, which has a symbol P. It has a symbol P. Phosphorus has a symbol P. If we were to pick these phosphorus to arrange them in subshell in its atomic configuration, you're going to have 1s2, 2s2, 2p6, 3s2, and 3p3. So if you are to sum them up, you're going to have 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 3 is 15. That gives you the atomic number of phosphorus. Then if you are to arrange them in the shell, KLO shell, you're going to have 2, 8, and 5. That's what you're going to have there. There are reasons why I said I'm going to do explanation more on the valency. Some elements have different valencies as of one thing, which I'm going to explain later, but then pay attention to the configuration. So the K shell will have 2, the L shell will have 8, the M shell will have 5. So the next one on the lineup is the 16 element that have atomic number 16. That is the sulfur. We're also familiar with this element sulfur. It has a symbol of X. Remember, it's different from silicon. Because I know most times now, if you ask students to write the symbol of sulfur, some will write it as Si. It is not Si, it is X. Now, if you are to write that of silicon, it's now Si. So if you look at the sulfur there, you have 1s2 at the subshell, you have 2s2, you have 2p6, you have 3s2, you have 3p4. Now, if you are to add them up, that is 2 plus 2. That is 4 plus 6, 10, plus 2, 12, and a plus 4. That gives you 16. That is the atomic number of sulfur. Then, if you are to arrange this sulfur, the electrons in this sulfur in KLOMONO shell, for sulfur, it's going to occupy only in KLOM. So you're going to have 2 electrons at the L, at the K, 8 electrons at the LO, and for sulfur, 6 electrons at the M shell. Then you go to the next one there is chlorine. I hope you are following. I don't want to rush things so that you can be able to follow what I'm saying or what we are doing. Chlorine has a symbol Cl. So when you are writing chlorine or you are seeing equation or formula where you see Cl, what to come to your mind that is talking about chlorine, because I don't think many people, when they are setting up questions or even some textbook, may not have time to start writing these elements in full. So they normally use symbol. So now chlorine is Cl. Then if you are to look at its subshell, you have 1s2, 2s2, 2p6, 3s2, and 3p5. If you are to sum them up, that is 2 plus 2 plus 6, 10, plus 2 is 12, plus 6, sorry, plus 5, that gives you 17. The atomic number of chlorine, that is 17. So if you were to look at the electronic configuration on each shell, what you have here is 2, 8, 7. And the valence is 2, 1 because it actually needs that one to bind. It just needs one to become a noble gas, to be stable. So that's why the valence there is 1. But I'm going to explain that more as a topic, that valency. Then, if we go to the next one you have there, that is the atomic number 18. Atomic number 18. We are so familiar with argon as an element. In fact, I want you to note this argon because most times when I ask students to use a short form to write electronic configuration using things like the argon, they do get confused. So argon has a symbol AR. Remember, the A is capital letter, the R is small letter. So when you are writing the symbol in exam and you write it A capital, R capital, remember, you're no longer talking about the argon. Now, if you look at the electronic configuration in the subshell for argon, you're going to have 1s2, 2s2, 2p6, 3s2, 3p6. That gives you, if you add them up, gives you 18, the atomic number of argon. Now, if you are to arrange this argon in K-LOM shell, the K will have 2, the L will have 8, and the M will have 8, meaning that it's a noble, it is stable. So that's why I have the valency of 0 there. It's not giving out anything, it's now stable. It is not giving out anything. That's why it's now stable. That's why I have the valency 0. Now, if you go to 19, you have the name of the element by that atomic number 19. It is there. Look at it there. That's potassium. Potassium has the symbol K. That's the symbol K. Now, if you are to arrange this potassium in its electronic configuration subshell, you're going to have 1s2, 2s2, 2p6, 3s2, 3p6, and 4x1. Now we've entered 4x. Remember the other one, there was no 4s there. We've entered 4x. So potassium with a symbol K, note it down. Where you see K, talking about potassium. Some people, when you ask them to write the symbol of potassium, probably because it started with P, they think the symbol should be P. No, some of these things may be a Latin word from where they get the symbol, but you have to note it down that the symbol is K. Now, if you are to arrange it in the shell, KLM shell, you're going to have 2 in the K shell, 8 L shell, 8 M shell, and 1 in N shell. Now, I've entered another shell. So if you look at the valence there is the valence there is 1 because of the element, that the electron at the atmosphere. Now, the next one should be the calcium. Calcium has atomic number 20. We are very familiar with calcium. What do I mean by familiar? At least some of you will just say, like, I need food that contain calcium. And when some people also want to go and buy drugs, they say they need calcium. So we are very familiar with element like calcium. The symbol is Ca. Remember, it is not C because we already have a symbol of C, that is carbon. So the symbol there is Ca. Now, this calcium, if you are to arrange them in the subshell of electronic configuration, you're going to have 1s2, 2s2, 2 pieces, 3s2, 3 pieces, 4s2. So if you are to add them up, you're going to have 20. If you go to the K-allo emulation, you have 2882. The valency electron becomes 2. So you can arrange it if you are drawing it. I think I've showed you how to draw it, to draw or to construct the electronic configuration. So you know where to put the 2, where to put and the 8 and all that. So the next one online is scandium. Scandium is the next one online. It has symbol as XC. It has symbol as SC. Remember that we already have an element that has symbol as X. So it's not when you see scandium now, you now say because you will now say because it starts with X, the symbol should be X. No, it's X. So that's C. Differentiate it from the sulfur that has symbol X. Though if you are to arrange it in electronic configuration, you have 1s2, 2s2, 2 pieces, 3s2, 3 pieces, 3d1, and 4s2. Now, I want you to understand something. Note something down now. By the time you get this scandium, the D block has come in. In future, we're going to discuss about the D block from elements of atomic number with 1 to 20. We did not see the D block coming. What we see there is S block and P block. S block and P block. But in that scandium, we've seen the entrance of the D block. Entrance of D block. Okay. Now, if you are to go take this scandium that has atomic number 21 to arrange it in shell, you will have 2, 8, 8, 2. Okay, 2, 8, 8 this. 2892 because it's a transition element. I don't want you to bother. We're going to treat transition element because of their variations. What happens in the quantum numbers? They have a lot of variations. There is what we call quantum number or their spinning. I'm going to explain that. We're going to treat it as topic. That's a transition element. They are very different. So I'm not supposed to take you up to this transition element because it has some complications which I will need to explain. But then, because I just have this diagram, you can limit your knowledge for now with this calcium up to 20 until when we treat transition elements so they can know why there is a lot of variations in their electronic configuration. It affects them. That's why we call them transition elements. So if you can be able to know from hydrogen to calcium, it will be okay. This other element that has the D block has some complications, which, except when we treat it very well, you may not understand the variations in their valencies, electron, and their electronic configuration. So let's look at the next slide, the next slide there is the shapes of these orbitals. So these orbitals we just mentioned, the x orbital, p orbital, d orbital, and etc. They have different shapes. They have different shapes. When scientists explain that wave function could be used to give information about this, about the electron. So wave function could be used to give information about the electron. That also helped us to explain their shape. But these things are done mathematically. But the area I want you to know for now is their shape. Forget about the mathematical aspect of the wave function. It will bring confusion into you. Now, if you look at the x orbitals, all x orbitals, they have the same spherical symmetry. When you say something is spherical, it's like football. You know, we are familiar with that. It's like football, or it's in a circle-like. So anywhere you see x orbital is in a circle-like. They can be represented by circle-like objects. However, they do vary in some ways. Now, for example, you have the 1s electron, which is most likely to be found at the distance from the nucleus. If you draw the nucleus of an atom, the distance from the nucleus to x of is not too far compared to 2s electron, which is mostly farther. You know, it's when you get the 1s electron, you move. You can now get the 2 electrons. You move. You can now get the 2p electron. Remember, it's farther. I'm talking about farther from the nucleus. That's if you measure the radius. Some of you that have done mathematics, circle, radius of a circle. Like I said, this thing is spherical. If you have done the radius of a circle, you will be able to know what I mean by distance from the nucleus, distance from the center to the circumference. That is radius of a circle. So to note the distance from the nucleus to where the 1s electron is located is different from the distance from nucleus to where 2 electrons are located, and so on and so forth. That's what I'm trying to explain. But what you need to note down there that I said is in a spherical shape, or in a kind of circle-like, or football. Can you all listen to that? Football. It's in a football-like object. Then we know we have these p orbitals. The density diagram for p orbitals are very different. The magnetic quantum number in M has only one value. This means that there is only one variety of x orbital. But for p, there are 3 possible values of magnetic quantum number, M. That word magnetic quantum number is represented by M. You can call it M, magnetic quantum number. So that magnetic quantum number shows that there are 3 types of varieties of p orbitals. 3 possible values of p orbitals, and that possible value is -1, 0, and +1. You know, so if you are to draw the shape of p orbitals, you're going to have 3 different shapes of p orbital, unlike the x orbital. Remember, then the 3 types of orbital, they point in different direction. If you are to draw it, you see that they point in different direction. They didn't point in the same direction. They point in different direction. It is very important you know that. Now, the next one you have there is the d. You have the d orbitals. There are 5 different types of d orbitals. But remember why I said until when I teach you more about D block. Why I tell you, I should, I tell you about your attention for now should be on the S and P orbitals. But that does not mean you should not know how to draw the D orbitals. Do you understand? That doesn't mean you shouldn't know how to draw the D orbital, the shape. I'm talking about only the shape. So we have about 5 different types of these D orbitals. When we say it on the well, let me not go there because by the time we start talking about this other transition element, I'll tell you more about these D orbitals. Then somebody might just be saying, what is orbital? Just an orbital represents a region of space in which there is a higher probability of finding electron. Of course, that's where that electrons are revolved. So don't get confused. They have the different name, they call them X, P, D orbitals, and etc. So what you have to note down now that I said the D orbital has different types and the P have different types, and unlike the S orbital. So let's look at examples of elements and their configuration again. If you look at why I bring this thing back, most times when you ask students that you can shorten, especially for elements that has a very long electronic configuration, there are ways you can shorten them for the purpose of, so that you don't get confused. Like I said some time ago, that when you give it to me in a short form, except if if I insisted, or if I insist that you should give it to me in full. So if you give it to me in a short form, I will still give you your mark instead of you failing it. Do you understand? Instead of you failing it. So I actually put this particular one to enable us know, know how these things can be done in a short way. Now, let's look at the atomic number. We have one atomic number, the hydrogen again. The element is hydrogen. The symbol again is H. The symbol again is H. Then the configuration is 1s1. That is not where our attention is. Then if you go to 2, we have the helium, which I told the symbol is He. Now the configuration is 1s2. Now I want you to note something down now. The next one, look at it carefully, look at it very carefully, look up. The next one there is the lithium. The lithium with the symbol of Li. Now, see what I've done there? I use the symbol of helium. I use the symbol of helium. Bracket it before I'll write what? 2x1. Someone may just be wondering, what did I actually do there? Or how come, instead of writing it the way it should be, I'm writing this. Now, 2, the helium stands for 2. That's what it means. For now, if you look at it, the element that has atomic number 2 is the helium. That's why we use the symbol 2. I don't know if you're understanding what I'm saying. Instead of us to begin from the beginning and get to the lithium that has 3 atomic number, I now use 2. I now use He. That He there stands for 2. Then if you remove 2 from an element that has 3 atomic number, what should remain is 1, right? So that is why we now put the helium bracket 2x1. I don't know if you understand me. Helium bracket 2s1. The 2s1 there is 1 plus the helium that is giving you the atomic number of lithium 3. The next one is atomic number that 4, that's beryllium. Beryllium that has Be. It has Be as atomic number, sorry, as a symbol. Now, if you go to the electron configuration, instead of writing it the way I explained at the initial time, what I use also is that helium 2. Helium, the symbol, I bracket the symbol, now write 2s2. So what it simply means that helium, as far as we are concerned, is 2 electrons plus 2, giving us 4, the atomic number of beryllium. I don't know if you understand what we've done there. It's very simple, just follow what we are doing. Then, if you were to go to the element atomic number 5, boron, with the symbol B, then we want to write its electronic configuration. We also use that helium. Check it properly. We use helium and now bracket right 2h2 and the 2p1. Meaning that if you take the helium that is 2, take the 2s electrons, that's 4 plus 1 in p, that is 5. That will give you the atomic number of boron. Then, if you were to take a look at the next one there, that is the carbon there. The carbon with symbol C and atomic number is 6. We also arrange it this way. You see, you have the He as the helium symbol plus 2s2 plus 2p3. That will give you 2 plus helium 2, that is 4, plus 2p2, that is 2p2, sorry, that is 6, giving you the atomic number of carbon as 6. Now, let's go to the atomic number, element that has atomic number 7, nitrogen. If you look at nitrogen there, the symbol also remains the N. Then you cannot see that we want to write the electronic configuration there. We want to write the electronic configuration there. What we did also use the helium as a symbol for 2, bracket it, remember, bracket it 2h2 for the nitrogen, 2h2 and 2p3. So if you are to add the helium plus 2, 4 plus 3, that gives you 7. That gives you 7. You know, that gives you 7. That's the atomic number of the nitrogen. Now you go to the next one, the oxygen. The oxygen with the symbol O. Then you have the helium is its electronic configuration again. Then you bracket the helium, you have 2s2, you have the 2s2 and 2p4. Meaning that if you add helium plus 2 plus 4, it gives you 8. That is the atomic number of oxygen. Now look at the element that has atomic number 19. Atomic number 19, fluorine, with the symbol F. You have the helium there and bracket it also. You bracket, you have 2s2, 2p5. So if you are to add it, helium plus 2 plus 5, that gives you 9. That gives you 9. So if you go to, then look at where we are now. I want you to underscore this thing, on the kind of put it in, lay emphasis on that. Number 10, the same way you pay attention, I ask you to underline helium. Underline this in neon. Now, the neon has symbol Ne. I'm repeating it again. It is not symbol Ne. Then, if you were to look at the electron configuration of this neon, what you're going to see there, the neon, you're going to see the helium bracket 2s2 2s2 2p6. So if you add the helium there, if you add the helium there plus 2s2, that is 4, plus 2p6, that is 10. Why I said you should pay attention to this neon, because we're going to use it in the same way we use helium. Now, if you look at that next element that has atomic number 11, which is the sodium. The sodium has the symbol Ne. Now, take a look at the electron configuration. Things has changed. I don't know if you can see it. Are you seeing it? Things has changed. Look at it very well. Things has changed there. So, what you're seeing there now is not He again. What you're now seeing there is Ne bracket. I don't know if you're with me, if you're getting, if you understand what I'm saying. It's Ne bracket. It simply means that it differs from the one He. So that Ne bracket, something has changed. Why is it that I decided to use Ne? That Ne stands for 10, the neon. So instead of you to write a long electron configuration, you can shorten it using this Ne. When you mention the Ne in brackets, you are simply telling us that that Ne is 10 electrons that is there. So it's unlike that He. The Ne there, bracket 3x1. Check it, look at it properly. 3x1. So if you were to check the electron that is involved in this sodium, that is 11. Neon 10 plus 1x, that is 11. So I've saved you the stress of writing a very long electronic configuration. So what you do, you just put down Ne. Remember, if you put down Ne, you failed it. I didn't say Ne. What I said, Ne bracket 3s1, giving us the sodium, and that is 11. Then the next one is the magnesium. If you look at the magnesium, you now see, if you are to write the electronic configuration there, I'm supposed to use this Ne bracket 3s2. That is, Ne stands for 10 plus 3s2. That is what? 10 plus 2, that is 12. Instead of you to begin to write 1s2, 2s2, what, etc., which, if it's an exam or if you are in a hurry, you may not be able to meet up, you can shorten the formula this way. Then that is then for that magnesium, you have a neon bracket 2 3s2, that is gives you 12. Aluminium, the same thing. You have neon bracket 3 for aluminium, 3s2 3p1. That is, if you add 2 plus 1, that is 3 plus 10. That gives you 13, which is the atomic number of aluminium. Then let's look at 14 again. The silicon with the symbol Si, the neon is also involved. The neon, that is the Ne. Remember, I didn't ask you to write it in full. What you are writing there is the symbol, which is Ne. Do you understand? So because it won't be wise, you now make mistake of writing Na, and something would have gotten the mark, you miss it out of more carelessness or thereabout. So the symbol there is, and you always observe that. So for the aluminium, you have the neon bracket 3s2, okay, we've passed a 3s2 and 3p1 for the aluminium. The silicon there is 14. You have the neon bracket 3s2, 3p2. That will give you 10 plus 14 plus 4, sorry, that is 14. Then you go to 15, the phosphorus. Look at it there, the neon bracket 3s2 plus 3p3. That's give you 15. Then go to chlorine. You have the neon bracket. You close the bracket, open the bracket, close the bracket. 3s2 plus 3p5. That gives you 17. Then let us go to argon. Take a look at argon. Argon, I said, has atomic number 18. Has a symbol Ar. Now, we'll get argon by neon, that's Na bracket 3s2 plus 3p6. That is 10 plus 2 plus 6. That gives you 18. Look at the next step there. Look at the potassium. Another thing has changed. Do you understand? Another thing has changed in the electronic configuration. You can now see, I didn't again use the neon. What I now use is argon, AR. Please, that's what I use. So don't use another thing. What I use is AR. I bracket that AR. Now write 4x1. So what the implication is this, that AR means 18, that's argon is 18, plus 1 electron, that is what, 19. So instead of you to begin to write, if it's an exam that's supposed to take like 30 minutes, you'll be writing like one qualification for 2 elements or 3 elements, and your time will be going. You can, if you understand this step, it will go a long way to help you grab the mark. Like I always tell you that any mark you see, make sure you grab it completely. Then if you go to the next one, the calcium with atomic number 19, calcium with atomic number 19, sorry, calcium atomic number 20, you have the Ar, that is argon, bracket 4s2, that is 18 plus 2, that is 20. So the same process continue. I will not treat this D block because magnetic quantum number cause a lot of variations in the electronic configuration. So I want to treat it as a separate topic so that you don't get confused. But if, like I said earlier on, if you can be able to get the electronic configuration up to the P, up to the X block, P block, for now, it will be okay, except when we begin to treat electronic transition element. But for now, if you can get the P block, how it's arranged, both in the elaborate form, except if you are asked in exam to write this electronic in full, they understand. But if there's no order to write in full, you can only use this to curtail or to use to minimize the time to meet up with the time of the exam. So I don't know. I believe we understand all the things. Getting what everything I've explained here. I explained the other one in full and also explained this one because there was time I was teaching something like this in the class. I was trying to use it in a short form. After the lecture, so many students were like, so this thing is difficult. That is why I decided to bring it again and take time to explain them in details. And if you can understand this now, I've just said now, it will go a long way to help you in any time you're writing, even when you're writing textbooks, if you are reading textbooks or if you are writing exam, it will go a long way to help you. So remember, we are working with time. So now, because of our time, we may not take so much elaboration, but what I want you to understand, I've been able to tell you how this element, there are different orbitals, p orbitals, x orbitals, d orbitals, tell you the maximum, how you can get the maximum of electrons that you there in each of them. Let's look at it now. The electrons are negative. Remember, I told you when we explain people that added to or that discovered the atomic particles. I know you can still remember it because not when you see it in the exam now, you get confused. There are people who say that people like Rutherford, their contributions to atomic theory, people like John Dalton, whatever they did, you still remember. But the people that discover electrons say they are what? Negatively charged. So always have that in mind because I know recently a student was asking me that he thought electrons are positively charged. So I felt confused when he asked me that question because I've taken time to explain that. So the electrons, remember, they are negatively charged particles and they revolve around the nucleus in a spherical region called the shell. They revolve in that shell or energy level. So you, like I said earlier on, you can have the K shell, the L shell, MO shell, NO shell, O shell. But if you can be able to at least learn up to any shell, it will be okay. Before we can start talking about element that can occupy up to O shell, you can now know that it could be as you go advanced. So their energy levels 1, 2, 3. Yeah, sorry, it's just 1, 2, 3. I made a mistake putting three twice. 1, 2, 3, 4, 5. That's their different energy level. So I've also explained to you how you will know, calculate the maximum possible number of electrons in each of these cells by using the n, two, that is n, 2n, 2n raised to power 2. So you can use it to calculate the maximum possible number of electrons you can put in any of this shell. It's very important. If you are confused, you want to put electrons in any of these shell, you're confused, you can make use of that formula to deduct or to compute the maximum possible electron that's supposed to be in any of these shell. No, I'm taking time to explain this thing because I know they are very, very important, you know. So when we talk about electronic configuration, it is difficult for you to study or to pass chemistry or to know chemistry without knowing how to arrange some of these things, arrange these electrons. So it's important as we are talking, even if you don't understand everything entirely, later you can quietly go through your notes, you can quietly study them one after the other. You know, it goes a long way to help you to understand them. So don't necessarily after the lecture you go and put down your notes somewhere. It is important. So before we are the summary, before we finalize, you know, some of you are saying I always want to give you assignment. The reason why I tend to give you little thing to do is not that I want to stress you or that I like bothering you. No. The reason is that I know that if you have something to do at home, it will help you to study that particular topic we've just discussed so that you don't just after listening to it go and put your note inside your bag. So I'm going to give you something to do, call it assignment. You're going to submit it when you resume. I didn't say you submit it online because if I wanted to submit it online, I put it in the LMS, but you're going to take time. Do it for me. You have to go into, why I say do it for me is I want you to do it for me. I want you to take time, the time you would have used to play or to sleep, take it to do for me. So this is the assignment. Number one, I want you to draw the shapes of x orbitals. Use your pencil. Like I said, if you don't have pencil, you can use the reason why it's always advisable to use pencils is that if you have a place to erase or if you have something to clean, it will be easy. But if you know you wouldn't have a problem of cleaning or erasing, you can use pen. You draw the shapes of x orbital. That's number one question. Number two, draw the shape of p orbitals. Remember, I told you how many p orbitals you have. So if you are drawing all of them. Remember, I said their direction differs. So the next one, number three, is draw the shapes of d orbitals. I told you how many d orbitals we have. Do you understand? So you draw it, let it be very neat, very, very neat. And just don't go and copy from somebody. Of course, you're not together. You can always do that in your own time, in your quiet time. Try to do it. Try to make it be in your brain. Then the fourth one there is, I want you to find the total maximum possible number of electrons in each shell. In each shell, have the KLOMNO shell. Find out, calculate for me. I hope you can be able to do that. Let me help you out. Use the symbol, the formula I gave you, 2 Na raised to power 2. So quietly at your own time, calculate what is the maximum possible number of electrons that are supposed to be in Kel shell, what is the maximum possible number that's supposed to be in L shell, and what is the maximum possible number that's supposed to be in M shell, what is the possible maximum number of electrons that's supposed to be in any shell up to just O shell. Do it for me. This is a simple assignment you can do at your own time, at your quiet time. So you wouldn't give excuses that maybe you whatever, but at least you are home. Even you can spare your time of time you're supposed to use in sleeping to do this thing for me. Then then some of these things I've told you, I know you note them down. But like I always said, I'm still going to give you the slide. And the slide, you will see it at LMS, at our LMS. You know, you have access to our LMS, you'll see it there. So why I'm going to put it there is to also enable those of you that are unable to capture in details the lecture, so they can take time also to read it, So you are going to get the slide there. I'm going to make sure I put the slide there for you. Then if in the course of reading them you have any question, you can also put the question in that LMS. I will look into it, I will check it, then I will get back to you. So I want to thank. Okay, if you have questions now, also you can type it on the side. On the chat line, you can type it. But if you something that you also need me to, if you something maybe in the course of you are reading your notes or you're going through your notes, you have other questions, we can always see when we see physically or in the class. Also, you feel free to ask your question. I want to. Okay, the assignment should be done in foolscap. Done in foolscap with your name, your department. The normal way we do assignment. This one should not be inside your note because you're going to submit it to me. And this is also going to help me to know people who are participating in our lectures, not people who just go home and be sleeping. Maybe tomorrow they'll start asking us what is happening. I want you to be active. There is no difference that you're home and here now. Just be active. Anytime we have lectures, just be active. If you have pressing questions, you can put it down any day, anytime. If you can put it on the chat, you can put it down. We'll get back, we'll solve it for you, or we'll reason it together. Or if there have places that are confusing you, always feel free. Do you understand? Always feel free. So do it in a foolscap sheet for me. Let it be, you have your rate your number, your name and department written on top of it. Thank you for listening, especially some of you that started with us and some that key in along the road, along the way. And I want to encourage you to continue to take your studies seriously. Thank you. Okay. The number four question, somebody is, the question number four is somebody asking, I said, find the total maximum possible number of electrons in a shell. The shell will have is K, L, M, N, O shell. And I said, let me help you out. You say you can use that formula 2Na square. That's 2n raised to the power 2. You can use it to compute the total possible maximum number of electrons you can see in each of the shells. Do you understand what I'm saying? So that will help you. If you don't know it, just use that formula. I explained to you that the N stand for the what? Stand for the energy level. 1, 2, 3, 4, and etc. and etc. Do you understand? So I think it's very clear, and if you do it, it will help you. If you do it, okay. The submission time, as soon as you resume physically, I want you to submit it. I don't want a situation whereby somebody will not say, I did not follow the lecture online. I was not told. Maybe that is why I did not do it. I'm giving the period from now to resume. No, it's a long period. So take time to do your this thing. And as soon as you resume, you submit it to me. Thank you very much. And God bless you. Have a wonderful day. We're going to meet again some other time.